Hey guys, this is Professor Janacek, and I want to go over a physical application of integration. I want to talk about work. Remember, work is force times distance, and for our situation, we'll use that W is equal to the integral from A to B of f of x dx, where F is our force. So, suppose a force of 10 newtons is required to stretch a spring 1/10 of a meter from equilibrium and hold that position. Now, according to Hooke's law, this force is given by f of x is equal to k times x, where k is a constant that measures the stiffness of the spring, and x is the position from equilibrium. So, might be good to remember Hooke's law, F is equal to k times x. So in this situation, we're looking at that. F of x is equal to k times x. Well, we have a force of 10 newtons, and that stretches my spring 1/10 of a meter. So this is our force. Here is our distance. So that gives us 10 is equal to k times 1/10. If we solve this for k, we get k, our constant is 100. So for this situation, we have f of x is equal to 100x. And we're going to need that for each of these parts. So part A, how much work is needed to compress the spring 5/10 of a meter from equilibrium? All right, so we have, of course, that f of x is equal to 100x. Now we are compressing from equilibrium, so we're starting at 0, but compressing it means we're going to go in the negative direction. And it's being compressed 5/10 of a meter, so we're going from 0 to 5/10. All right, and our work, we're going to integrate. Well, it'd be the integral from 0 to negative 5/10. We begin at 0 and we end compressed by 5/10 of a meter. And then our integrand is our force, 100x. And we're integrating with respect to x, so our differential is dx. Now, traditionally, the integral is not defined when we go from the larger limit of integration to a higher limit of integration. So what we'll do is, if we want to turn those around and go from the smaller to the larger, that's fine as long as we negate the entire integral. So it's going to be the negative integral from negative 5/10 to 0 of 100x dx. Pretty straightforward integral to do. I'll let you take a moment and give that a shot. You should end up with 12 and 5/10. This is work, so this will be in joules. All right, moving on to part B. How much work is needed to stretch the spring from spring 2500 meters from equilibrium? So the first one, remember, we were compressing it, but here we are stretching it. We're still using f of x is equal to 100x, but now we're going to go from equilibrium, 0, to positive 2500s. So we're stretching it. It's the same situation though. We're going to integrate from 0 to 2500s of our force, 100x. dx on there. Another pretty straightforward integral to work through. You should end up with, take a moment and go through that, but you should end up with 3 and 125 thousandths. Again, this is in joules. All right, now on to part C. How much additional work is required to stretch the spring 2500ths of a meter if it has already been stretched 1/10 of a meter? So in this case, we are stretching it, but we want an additional stretch. So again, let's make note of our force. F of x is 100x. But now it's already been stretched 1/10 of a meter, so we're going to start at 1/10 and we're going to stretch it an additional 2500ths. So the place we're going to end is going to be that 1/10 plus the 2500ths, so we actually end at 3500ths. So be careful with that. That's the important bit here. That's what makes this one different from the two above. We're not starting at 0, and we're not even given where we end. We have to compute that. But after that, it's pretty straightforward. We're going to integrate from our starting point, 1/10, up to our ending point, 3500ths. Our force is still 100x, and our differential is still dx. Integrate that. Again, quite straightforward, I think. Integrate that. We should end up now. Let's think about this. We are going an additional. So this part B, we stretched. It was stretched 2500ths, and we ended up with a little over 3 joules. Now here we've already stretched it. It's 1/10. Actually, let me back up. Hold on. Where was I saying? Okay. Here. It took. Well, okay. The first situation up here, it went 1/10 of a meter and it took 10 newtons. All right. So that's a bit of force to move it 1/10 of a meter. In example part B, the part B of this example. Here was just from equilibrium, we went 2500ths, but now we're going 2500ths past something. So we already had to get it to 0.1. That was a bit of work, but it's going to take even more work for us to go that additional. So this one, whatever you come up with, should be greater than what you got in part B. And if you do all the computations properly, you should end up with, I believe, 5 and 625 thousandths. So again, this one, because it's an additional stretch, should be a bit more than the previous example. Hope all that's clear. Enjoy!